Good morning, everyone, and thank you all for joining the 2026 ReEDS user group meeting. My name is Vincent Carag, and I'm a researcher here at the National Lab of the Rockies and the developer of the Regional Energy Deployment System, or ReEDS. So over the next 50 minutes or so, I'll be presenting an introduction to the ReEDS model, splitting the presentation into three major sections. We'll start with a brief model overview explaining high level what ReEDS is and how ReEDS works. We'll then go over key outputs and inputs of the model. And then lastly, we'll dive deeper into some key model features to better understand how ReEDS goes about its decision-making. So jumping right into it, we'll start in section 1 with the question, so what exactly is ReEDS? So the name ReEDS is actually an acronym that stands for the Regional Energy Deployment System. So contrary to what you might expect, the first RE of ReEDS doesn't stand for renewables, but instead refers to ReEDS being a zonal capacity expansion model designed for the contiguous or lower 48 states of the US. So some additional details about the model. It's fully open sourced, downloadable on github.com, with new versions of the model being released every month. ReEDS traces its origin back to 2003 with the wind deployment system. This was NLR's original electric sector capacity expansion model, primarily focused on wind technologies. But since then, ReEDS has gone through several iterations and rewrites to now include several other generating technologies, including but not limited to hydrocarbons like coal, natural gas, and oil, nuclear technologies, other variable resources like solar and hydropower, small scale and emerging technologies like biopower, geothermal, hydrogen, and storage techs like utility scale lithium-ion batteries and pump storage hydropower. Also, since 2003, ReEDS and its predecessors have been used as the primary model for hundreds of different studies, both at NLR and by external users. So earlier I described ReEDS as a capacity expansion model, which refers to the model's main function of deploying and operating various capacity assets. These would be things like generating technologies, transmission lines, and energy storage units to meet future demand of the US power sector. The decision-making of where, how much, and when each of these assets are deployed and operated is guided by a least cost optimization performed over future model years. The objective of this being to minimize the total capital and operational cost of the system, subject to a variety of electricity price forming, technological, and operational constraints. So in effect, ReEDS is structured as a massive optimization problem, complete with its own set of inputs, variables, model constraints, an objective function, and outputs. So on screen is a basic flow diagram showing an overview of the necessary inputs and expected outputs for every ReEDS simulation or ReEDS run. As you can see in the left blue box, ReEDS has many different inputs. I'll cover them more in detail in section 2, but at a high level, these inputs include things like existing and planned generation and transmission capacity, giving the model a baseline representation of the US grid to start with, spatiotemporal generation profiles and supply curves for energy sources like wind, solar, and hydropower, technology availability and performance projections, additional cost projections for capital, O&M, and fuel costs, reliability criteria, federal and state policies, and of course, hourly load projections for a variety of different model zones across the contiguous United States. In addition to these inputs, like any optimization model, ReEDS also includes various constraints to the objective function, which you can see in the light blue box at the top. These constraints include things like price forming constraints, primarily affecting system costs for serving load, which include load generating balancing, reserve requirements, and regional policies. Additional constraints govern technological behavior within the model, which include but are not limited to physical and operational constraints, ensuring realistic deployment and operation of the capacity assets, fuel supply considerations, and build and retirement dates governing when capacity can be taken offline from the system. Along with these inputs, these constraints are fed into the main objective function of the model, and for each future year, the model optimizes for the least cost portfolio of assets required to meet the future demand of the system. So some of the main ReEDS outputs can be seen in the right yellow box and include additions and retirements of generation and storage capacity in each model solve year, transmission capacity additions, operational data like tech-specific energy generation, curtailment, and operating reserve values, fuel consumption, and of course, the overall system costs, as well as electricity prices and retail rates for the system. Okay, so we're jumping into the second section of the presentation now, where we dive deeper into the key inputs and outputs of ReEDS. And like last year, I'll be starting with the outputs in order to give you all an understanding of what to expect from model results. And then afterwards, we'll go back and look at the inputs to better describe how to set up ReEDS scenarios and how your selection of inputs will affect model outputs. Okay, so first and foremost, on the outputs, ReEDS provides data on the generating capacity and total generation over the model simulation horizon, which by default is from 2010 to 2050. On screen on the left, you'll see the final 2050 generating, storage, and transmission capacity of the United States electricity system for a generic ReEDS run. And to the right is a plot showing the evolution of that total capacity. Going back, if you look at the left map, you'll see a bunch of stacks of colored bars. Each stack represents the total capacity of each model region, and each colored bar represents the share of regional capacity for a particular technology. Summing all these stacked bars would give you the total capacity of the US system in 2050, which is a little over 2,000 gigawatts, as shown on the far right. I'll just point out here that although ReEDS begins its optimization in 2010, for simplicity, most of the results I'll be showing today will have start dates in present day 2026. I'll also want to point out here that all the outputs shown in this presentation are for illustrative purposes only. They don't represent default ReEDS results and are used exclusively for examples of ReEDS outputs. So, as alluded to by the map in the previous slide, ReEDS uses its high level of spatial resolution and flexible zonal definition to show users not only how much capacity is deployed each solve year, but where that capacity is being deployed. So on the left are examples of two different ReEDS results presented at two different spatial resolutions. One shows the solar capacity deployment from 2020 to 2050 at the state level. The other is an example of natural gas deployment in the Western Interconnect shown at the county level. ReEDS is also capable of further downscaling spatial results for certain technologies. This is seen on the right. This is an example of site-level wind and solar deployment, which is created by a module run post-ReEDS optimization that maps capacity deployment of these technologies back to their corresponding supply curve points. So, along with other capacity assets results deployed by ReEDS, the model also outputs the evolution of transmission capacity. The left plot shows the quantity of interzonal transmission, which is transmission built between zones in ReEDS. ReEDS also does output quantities of intrazonal transmission, which is transmission built within each region that links site-based generation like wind and solar to the rest of the transmission network. It's not shown on any of these images here, but that information is available. And like generating capacity, ReEDS is able to use its spatial capabilities to visualize both the magnitude and type of transmission between zones. So the maps on the right show two examples of future transmission networks, where the line color indicates the type of transmission infrastructure and the line thickness indicates the transmission's capacity. ReEDS will also output several cost and price metrics. These mainly include the net present value of the system cost over the model horizon, seen in $1 billion on the left. This value effectively is a representation of the objective function, where each of the colored bars represents a capital or operational cost that ReEDS aims to minimize for each solve year. ReEDS also calculates additional energy service prices like the marginal energy price by summing prices of ancillary services, state renewable portfolio standards, renewable energy credits, and CO2 emissions prices. ReEDS will also calculate annualized system cost of the electricity system, seen here in the center, by dividing the total system costs on the left by the total delivered energy for each model year. This is the main metric used by the ReEDS team to report cost trends over time. We could then take this metric even further and use another post-optimization module to apply additional transmission, distribution, and administrative costs to estimate an annual retail rate of electricity expected for a typical residential customer. Last on our example outputs, ReEDS reports various metrics related to emissions and health impacts. Emissions are tracked for all combustion-based technologies like hydrogen turbines, biopower, coal, gas, and oil. These emissions include carbon dioxide, methane, sulfur dioxide, and various other nitrous oxides. And these emission levels can be used in complex air quality and concentration response functions to estimate human health impacts, which is reported in terms of emissions-related monetized damages and mortality rates. So now with an understanding of the different outputs you could expect from the model, let's back it up and dive into the key inputs used by the model to perform its optimization and calculate these results. So to start, ReED starts with a baseline representation of the 2010 electricity system of the US, composed of existing and prescribed generation and transmission assets with data on their types, locations, their capacities, various operational parameters of the fleet, like heat rates, FOM, VOM, and water cooling needs, as well as planned retirement dates. Generation data is sourced from the US Energy Information Administration's National Energy Modeling System, which is also updated annually in the model. And by default, the transmission capacity is provided at the default 134 ReEDS model zone resolution and is sourced from the 2021 North American Renewable Integration Study. So now that we've established a baseline representation of our system, we'll also want to know how much energy the system will need to produce for future years. So another key model input that captures this is the future electricity demand or the load. Um, ReEDS has a large selection of spatiotemporally resolved scenarios to choose from, representing a wide range of potential load futures for the model to optimize for. Within each load scenario are annual load growth projections of the entire US electricity sector. You could see on screen in the lower left examples of a generic low, medium, and high load projection. Each load scenario will also include 40 years of hourly load profiles spanning from 2010 to 2050. And within each of these 40 load years are hourly profiles for 15 different weather years, allowing ReEDS to capture a variety of weather conditions for each solve year. So an example of this data would be up in the top right plot. This top right plot shows the 8760 hourly load profile of a county in Wyoming for one of these load years fit to the 2023 weather year conditions. Load scenarios differ both in their hourly load characteristics as well as their locational demand values. Seen in the upper left plots are the average day monthly demand for a 2018 reference and high load scenario. Notice how not only are the load magnitudes different, but each scenario also have different load shapes, where the high load profile experiences or sees more pronounced peaks in the late afternoon, evening time for each month compared to the other two. The lower right plot here reinforces that ReEDS load profiles are spatially resolved and that the model aims to balance load for every model zone as opposed to just balancing a single total national load. Moving on, ReEDS includes various assumptions for technology cost and performances, which mostly source from NLR's annual technology baseline, or ATB, which is also updated annually. So on screen are the default ReEDS CapEx cost assumptions for various ReEDS technologies grouped by their major tech category. In addition to CapEx cost, each technology pulls additional inputs from the ATB, seen on the right. These would be things like O&M costs, heat rates, construction times and schedules, as well as various financing assumptions. And each technology input also has a conservative, moderate, and advanced cost trajectory from the ATB, which allows users to mix and match parameters based on how they want to set up their model assumptions. Lastly, here I want to just mention that ReEDS does include assumptions on fuel cost projections for various technologies. These are sourced from the EIA's annual energy outlook, and we'll dive deeper into these assumptions in section 3. Okay, so variable renewable or resource availability. So ReEDS uses high resolution data on the spatial and temporal resource availability to model generation potential of variable energy generators. These would be things like wind, solar, hydropower, geothermal, etc. Starting with the temporal availability of the data, this refers to at what times a resource is available and how much is available. So using the examples of wind and solar power, wind speeds and solar irradiance data is taken from models like the NSRDB and Wind Toolkit, and generation potential is calculated for solar and wind for over 50,000 sites across the country using the REV model. From there, these generation potentials are then converted to hourly capacity factor profiles, which you can see on screen, which the model uses to determine when and how much these technologies can generate. It's also important to capture the spatial availability of these profiles, i.e. where the model is allowed to deploy these technologies. So when producing the capacity factor profiles on the left, the REV modelers will also consider various land exclusion layers to determine where technologies like solar and wind can be developed. These layers include setbacks for existing infrastructure, habitat protection, and many others. Additional land exclusion layers are then added or removed to develop different accessibility scenarios for users to choose from. So seen on screen on the right are examples of 3 different siting scenarios for utility scale PV and land-based wind. Starting with the reference case, this is our default case for land availability. We have the open access case representing roughly double the generating potential of the reference case, as well as the limited access case representing about a third of the generating potential of the reference. And then, though not shown on screen, additional data and assumptions are used for other techs mentioned earlier, like hydropower, geothermal, biopower, etc., and that these technologies vary in development procedures from wind and solar. Okay, so the last major ReEDS input I'll cover are some of the federal and state policies that ReEDS models. The ReEDS team tries to update these policies quickly and frequently to ensure the model represents as many active policies as it reasonably can. At the regional and state level, ReEDS includes known state mandates and renewable portfolio standard requirements, technology restrictions, enforced retirement dates, policy retirements, regional trade restrictions, and local emissions restrictions. And then at the national level, ReEDS models additional policies that include things like national emissions restrictions and technology-specific tax incentives, which include changes made to the tax structure by the One Big Beautiful Bill Act in the summer of 2025. These are all the inputs and outputs that I want to cover in section 2. I hope everyone now has a better understanding of the major considerations that the model takes when performing its capacity expansion planning, and what types of results you can expect from the optimization. So we'll now be shifting the presentation to cover several key model features that'll help you better understand how the model operates and represents different aspects of the energy system that it simulates. From here, we'll start with the components of the objective function. So as mentioned in section 1, at the core of ReEDS is an optimization problem designed primarily to minimize the total present value cost of system investments and operation. The major components of the system costs are the following costs on screen. These are generally grouped into 4 major categories, starting with the investment costs. These would be the capital costs of generation, transmission, and storage. You've got operational costs, such as like fixed and variable costs associated with the operation of the system over the evaluation period. These costs are accounted for in the optimization by converting them to a net present value using a 30-year capital recovery period, which assumes that the cost stays consistent over the economic lifetime of the investment. You've got ancillary service costs for various services that the model needs to provide and pay for, like spinning, regulation, and flexibility reserve products. And of course, you have policy payments that must be paid for by the system for things like alternative compliance payments, CO2 taxes, or model-specific penalties that may act as proxies for institutional or industry barriers. These would be things like penalties to the objective function for rapid capacity expansion growth, siting and permitting limitations, etc. The objective function of ReEDS also accounts for the financing aspects of new installed capacity by taking the infrastructure's overnight capital cost and applying financial multipliers that vary by technology. So these would be things like interest accrued during construction phase, tax rate and tax credit policies, debt to equity ratios, and others. And then lastly here, I want to emphasize that the levelized cost of electricity and electricity prices are model outputs of ReEDS. They're not model inputs. ReEDS doesn't take in electricity prices. The use of LCOE would require the assumption of a capacity factor for generating technologies, or in other words, an assumption on what percentage of the year a plant will operate. But in its optimization, since ReEDS determines how much each technology generates during its optimization, the amount of electricity generated and by what technologies that ReEDS decides is actually what determines things like electricity price and LCOE. So it's more of a model output than an input. Okay. Another important component of the overall ReEDS optimization are the key constraints. So on screen, there are 7 of the key constraints that the ReEDS models is forced to abide by. You may recognize some of these from the light blue box in my second slide of section 1, if you could remember. Starting with the load balance constraint, this is basically boils down to generation has to equal load. It's the central constraint of the model, stating that in each model region, ReEDS must either generate or import enough energy to supply that region's load at all times. So this constraint ensures that all model regions have all loads served at all times and allows the model to build additional capacity or capacity expand if the existing system can't serve load. The following 2 constraints build off of this load constraint, ensuring the model provides adequate reserve targets. Um, you have the planning reserve constraints, ensuring that the model has built a system with sufficient firm capacity to meet resource adequacy targets, as well as operating reserve constraints that ensure sufficient generating capacity is built to provide ancillary services, things like load following reserves, regulation, or contingency. Basically, generation that's on backup and ready for any outage or issue or fluctuation on the grid. The next 3 constraints ensure realistic operation of the capacity assets deployed by ReEDS, starting with the generator operating constraints. These ensure that generating technologies operate according to their physical or operational limits under realistic conditions, informed by the characteristics provided. So some of these constraints would include things like storage technologies need to abide by their state of charge limits, that thermal generation potential be informed by the heat rates of the technologies, or that hydropower generating potential reflects monthly variability of the stream flows. Similarly, resource availability constraints ensure variable generation potential is limited by spatiotemporal resource availability that we provide. This would be examples of like ensuring that solar isn't generating at night, or that wind turbines won't be deployed in regions that have insufficient wind speeds. Um, Lastly, we've got transmission constraints, ensuring that energy flows between regions respect transmission limits, and that the additional energy flow between regions would require investments into the capacity of the transmission network. And then last of the 7 major constraints, ReEDS optimizes the system within the bounds of various policy constraints, ensuring the system build out meets various emission targets or capacity generation mandates. Okay, so moving on. ReEDS has a comprehensive selection of generating assets it can invest in to serve load, each with unique, detailed representation of their operational characteristics. So on screen is a fairly comprehensive list of generating and storage technologies that are represented in ReEDS, organized by major tech categories. Starting off on the left in the green box is our hydrocarbon section, containing the generating technologies fueled by oil, natural gas, and coal. So as you can see, ReEDS represents and deploys several different configurations for each of these technologies. most of which can also be retrofitted with or deployed with carbon capture and storage technologies to achieve emissions targets. In the top right blue box, you'll see that ReEDS can represent both large-scale light water nuclear reactors, as well as deploy new small modular reactor designs. Geothermal technologies are classified by well depth and site generation potential. Storage technologies include utility-scale lithium-ion batteries and pump storage hydropower. Speaking of hydropower, ReEDS can also simulate a variety of different hydropower generating technologies, including run-of-river and powered reservoir-based configurations, as well as have the capability to upgrade non-powered dams. And of course, ReEDS also represents a host of technologies that operate on variable resource availability, including single-axis tracking, utility-scale photovoltaics, fixed tilt behind-the-meter PV, concentrated solar power, and on and offshore wind technologies. And lastly, ReEDS includes other technologies that serve a variety of different system needs. These would be things like landfill gas, biopower, which can be used as a primary fuel or co-fired with coal, demand flexibility technologies, hydrogen production technologies like steam methane reformers and electrolyzers, as well as hydrogen fuel combined cycle and combustion turbines. Going further into detail of technology representation in ReEDS, technologies in ReEDS are further categorized and then clustered by vintages, which are designations of same technologies that have similar cost and performance characteristics. This is done to help simplify model formulation with minimum change to the results, allowing ReEDS to consider and operate clusters of technologies as a single aggregated capacity with a set of characteristics. So starting with the existing hydrocarbon and nuclear generators, these are binned into historical vintages by technologies with similar heat rates for each balancing area. The number of bins is user specified, and the number of bins in each region can actually be increased until each bin basically consists of an individual unit. This unit level representation of the historic fleet is possible and does provide better resolution, accuracy, and tracking of the historic fleet, but it heavily increases computational complexity of the model, making it harder to solve. New capacity built endogenously by ReEDS are vintaged by solve year, where a user can specify the vintage of each technology for each year. So, for example, you could create one vintage for like gas CT spanning from 2025 to 2030, and then specify a different vintage with different characteristics for gas CT spanning from 2030 to 2035. Then if ReEDS builds gas in 2027, it'll inherit the performance characteristics of the first vintage. And then if ReEDS builds gas CT in 2032, it'll inherit the characteristics of the second vintage. Variable resources are also vintaged, and they're even further subcategorized by resource quality, as well as cost to interconnect them from the REV site to the grid. Okay, so as alluded to before, ReEDS has a variety of different spatial resolutions that it uses for defining its balancing area and modeling constraints. So on screen are different zonal aggregations used within the model, along with corresponding input data or constraints that it's used for. They're generally ordered on screen from left to right and then from top to bottom in decreasing resolution or increased aggregation. Starting in the top left, this is our highest resolution in ReEDS. These are the 50,000 REV sites. As stated earlier, these are used for determining things like resource availability and cost to connection for technologies like solar and wind. Reading from left to right, we also have our modeling resolutions, and these are the resolutions that ReEDS mainly uses for like load balancing. So the first of the three is the county level resolution. This is our high resolution modeling resolution used for modeling sections of the full CONUS system. The upper right here is the one y'all are most likely familiar with. These are the 134 model zones of ReEDS. They're collections of counties that generally follow historic balancing authority areas, though not exact. This is the default ReEDS resolution that many of y'all are familiar with, where most of the major constraints are enforced at. Additionally, these zones respect state boundaries as well, which means they can be aggregated to our third load balancing resolution, which is the lower 48 state resolution. This is used for more simple, more coarse load balancing to reduce model complexity when simulating high complex constraints. But it's also helpful in enforcing state level policies like renewable portfolio standards, emissions regulations, technology bans, etc. The rest of the spatial resolutions on screen are some form of aggregation of the 134 model zones, and they're used for a variety of different constraints that are enforced at a more broad level. These would be constraints like gas supply curves or fuel supplies enforced at the census division level, or the interconnect level enforcing the different transmission type restrictions. Okay, so now let's talk about representative time periods. Due to the complex spatial and temporal scope of the contiguous United States, by default, ReEDS doesn't optimize investments and operations over a full 8760 hourly temporal resolution for a year. Instead, it optimizes over a set of representative periods, which are in the model are typically days, broken up into aggregated hourly chunks. So these representative periods are selected prior to the model solve using a two-step optimization. First, a user-defined number of periods is selected, and these periods represent the full year with minimum deviation to regional wind and solar capacity factors, as well as energy demand for the complete 8760 time series. Next, each actual period or each actual day of the year is assigned to the representative period it most closely resembles, and weights are calculated for each representative period corresponding to the fraction of the year that that period represents. So in case that was as clear as mud to some of y'all, I'll give you an example. So by default, ReEDS uses 33 representative days at 3-hour time chunks as its representative periods. So what the model will do is it'll find the 33 days in the year that most closely represents the full 365 days of a solve year. These would be the ones that are like highlighted in the top image here. And then it'll solve that year over those days at 3-hour resolution. It'll then assign each actual day of the year to one of the 33 representative days that it most closely resembles to produce the full 365-day solution for the year, which you see as like the full top photo on it right here. So like I mentioned, 33 representative days at 3-hour time resolutions is the default for ReEDS, but both of these options can be changed. You could use 5-day periods as opposed to single-day periods. This is a coarser representation of the year, but does provide necessary detail on inter-period operations like inter-day storage operations and things. You can also represent the year as a full 365-day resolution, so basically like no representative periods. This is possible, though this option doesn't work out of the box in ReEDS because it makes the model computationally expensive to solve. It would require you to make compromises to the model formulation elsewhere, like lowering the spatial resolution or decreasing the use of features that complicate the model formulation. Okay, so since ReEDS by default uses representative periods to solve its optimization, it doesn't capture all actual time periods of the system's operation, and thus may not be sufficient in assessing that system's resource adequacy. Or the system's ability to meet load plus planning reserve requirements. So to assess resource adequacy, a ReEDS run will employ one of two methodologies in its run. The first on the top is the capacity credit method, where for a given solve year, which is like resembled in a box, ReEDS designs a system and then passes that system to a capacity credit module that calculates firm capacity of existing resources, as well as the marginal capacity credit values for any additional resource. After performing these calculations, or ReEDS will then move to the next solve year and perform that same procedure, again, calculating firm capacity and marginal capacity credits for the system for every single solve year. And then once performing the calculations on the final solve year, the user can choose to run like a dedicated resource adequacy model, like PRAS, on the final system, though this is not necessary. Moving down to the bottom, the stress period method below is the resource adequacy assessment method that ReEDS uses by default, though. In this method, the PRAS model is actually brought into the optimization of each ReEDS solve year, and then it iterates with the system design optimization of ReEDS until ReEDS is able to build a system that meets the resource adequacy targets specified by the user. So stepping through this briefly, at the beginning of the solve year, ReEDS will design the system by optimizing over its representative periods and then pass that system into PRAS. PRAS will then conduct a resource adequacy assessment to determine two things. The first of which is a collection of stress periods. These would be the periods with the highest risk of unserved energy. And second, it will determine whether or not the system meets user-defined resource adequacy targets. If the system doesn't meet these targets, PRAS will then pass ReEDS the collection of stress periods to include with its representative periods, and then ReEDS will optimize again, this time considering the new periods of high unserved energy. We'll dive deeper into the stress period method formulation briefly, but first we'll go over some details of the upper capacity credit method. So in this next slide, we'll go through how the capacity credit module actually calculates the firm capacity and marginal capacity credit for each solve year. It starts by taking 7 years of hourly load data at the planning region resolution and splitting that load profile into either hours in the hot season or the cold season. Then for each season, organize the hours from highest hourly load to lowest to create the load duration curve, which is this black line here on the right. The model will then subtract generation of existing variable generating sources at each hour to generate the net load duration curve, or NLDC. This is the red solid line here, and then subtract the generation of another incremental addition of variable generating capacity to calculate the NLDC delta, which is the dotted red line here. The model will then take the 100 hours of highest load and calculate this dark blue area between the LDC and NLDC. This would represent the capacity value of existing variable resources. And the light blue area is also calculated between the NLDC and NLDC delta. This would represent the marginal capacity value. Then by dividing both these values by corresponding installed capacity and the number of highest load hours, the module gets existing and marginal capacity credit of the technologies, which are the metrics that are passed on to the next ReEDS solve year to inform investment decisions. Okay, going back to the stress period method, this slide's more of a detailed step through of the procedures for the stress period method, but including illustrations to better understand the iterative approach and what it actually does. So in the stress period formulation, prior to the optimization start, ReEDS will select initial seed stress periods to include in optimization. This will include periods with minimum average solar and wind availability by interconnect, as well as peak load periods by planning area. Moving to step B, ReEDS will then conduct its optimization of the solve year, aggregating its results to planning subregion before passing them into PRAS. PRAS will conduct its resource adequacy assessment over each planning subregion using hourly dispatch over 7 years of weather data. It'll calculate each subregion's normalized expected unserved energy, which is used as the metric for determining a system's resource adequacy. PRAS will then determine if all subregions' NEUE is below the threshold that the user defines. If not, like in this example, PRAS will then identify periods with the highest level of unserved energy and then pass these new stress periods back into ReEDS to re-optimize, now considering these stress periods. Step B through E will continue the repeat until until either the NEUE in all subregions is below the threshold, like you see here in step F, or if the maximum number of iterations set by the user is exceeded, at which point the model will move on to the next solve year and start again in step B. So as stated before, for operating reserves, ReEDS models ancillary services to the system. providing regulation, spinning, and flexibility services meant to handle grid fluctuations and larger contingencies, disturbances, or outages. The requirements for each service depends on how much wind and solar or how much load is on the grid at any given time. ReEDS also assigns ramp rates to each of these technologies, providing operating reserves to determine reserve provision capabilities. To represent the operating reserve products as three distinct types like seen here, this is actually an alternative option. By default, ReEDS will model a single generic product that combines the three products into a single hybrid this is done to reduce model size and improve runtime. Lastly, the objective function of ReEDS will optimize between letting a technology provide energy or provide reserves, and it'll consider the opportunity costs associated with the technology providing reserves over load balancing based on a few things. First, that technologies are only allowed to provide reserves if there's free capacity that isn't already contributing to meeting load. Second, that the available capacity from neighboring regions can contribute to reserves only if there's sufficient transmission to do so. And third, that storage technologies can contribute to reserves if there is available energy in the storage to do so. Shifting gears back over to some technology features, ReEDS is capable of accounting for and constraining model results by cooling water availability, as well as the needs of cooling water-dependent technologies. This allows for ReEDS to have a more accurate representation of the thermal fleet operational characteristics, as well as better consider real-world external factors to electricity generation, things like future water availability. So it'll do so by first assigning each cooling water dependent generating tech a cooling technology, as like the ones you can see up here, as well as a water source to draw cooling water from. Some examples seen below here. During optimization, ReEDS would consider how much water is required for the desired operation levels of each generating tech, and then the model will ensure that the water needed for the operation is below the limits defined by a regional water availability supply curve. Users who are interested in using this feature would need to make compromises with model complexity and scope, though, as this feature is computationally expensive, but available. So as mentioned earlier, ReEDS uses a unit level database for defining existing pre-2010 generating and storage fleet, as well as any post-2010 prescribed builds and retirements. Users can go in and manipulate this data set to enforce exogenous capacity for the model to be built, as well as enforce different unit level scheduled or lifetime retirement dates. Users can go into the database and explicitly define retirement dates for any existing or prescribed builds that are in there. There are also options that enforce sweeping changes to retirement dates. Options like the ability to shorten or extend coal lifetimes, or to be able to choose between different nuclear retirement scenarios. ReEDS will also choose to endogenously retire capacity if either a specific fraction of the FOM costs are not fully recovered, or if not dispatched above a certain capacity factor in a given solve year. So coming back to fuel prices, coal and uranium fuel prices are defined exogenously at census division level and have a single reference price scenario, reflecting the relative inelasticity of the fuel price. Static natural gas prices can also be defined exogenously, but contain an additional low and high gas price sourced by the EIA's annual energy outlook and updated annually. By default, though, ReEDS actually models natural gas prices elastically and links fuel prices to demand via formulation that considers both regional and national elasticity coefficients to determine changes in fuel prices in response to electric sector natural gas demand. There are three different calculation methods for endogenous natural gas fuel price shown on screen. We'll skip the first bullet point because this is basically the fixed price natural gas formulation. But starting with the second bullet point, this formulation uses a national supply curve with census division multipliers to differentiate regional fuel prices. This next option is a census division supply curve formulation. And then lastly is the default formulation, which are supply curves with national and census division components. ReEDS will also adjust natural gas prices for high electrification scenarios to account for the presumed increase in gas usage outside of the electric sector. And lastly, hydrogen fuel prices can be defined either exogenously by the user or endogenously in the model, and is based on the gas efficiency of hydrogen producing technologies like steam methane reformers or electrolyzers, as well as the natural gas price per census division. Okay. Oh, wait. There we go. So we've already spoken on some of the policies within ReEDS, but I wanted to quickly flash this slide to give you all more detail on the flexibility of policy options that ReEDS can model. The ones that are active by default are the enacted tax credits. These would be things like production tax credit, investment tax credit, 45Q, 45V, and all other changes from the One Big Beautiful Bill Act. State level clean energy policies like renewable portfolio standards or clean energy standards. There are also regional and state emissions policies like SB 100, the CASPER or cross-state air pollution rule for nitrous oxide trading limits, EPA's greenhouse gas regulation, as well as various other technology mandates and state-level forced retirements. There are other additional options to explore alternative policy formulations. These would be things like flexible emissions caps, emissions taxes, and national generation requirements. And then a quick note that the representation of these policies are generically defined in ReEDS to allow for flexible implementation and allow the user to explore a variety of different policy scenarios when running ReEDS. Okay, so this is the last slide of actual content I plan to cover for this presentation. And with that, I want to pull together everything I've covered so far and give like a high-level walkthrough using this process flow diagram of what actually happens when you hit go on a ReEDS model. So starting on the left, we have this launch script called run batch py that takes in a case file. So this case file is it's either a case or a list of cases where the user identifies various input options that we covered in section 2 to be included in the model runs. So this is where you would determine things like which load scenario to use or which technology cost assumptions, policy scenarios to use or include into your run. And then so it'll be ingested into the launch script, and then the run will be kicked off. So once the ReEDS run is kicked off, a set of input processing scripts will read in the case file, and then it'll pull the correct model data from the ReEDS repository, manipulate it, and then reformat that data to a format suitable for the GAMS written portion of the model, which is the orange sections. The input files then move to the model setup portion of ReEDS, where the data is declared into GAMS data structures. This part of the code also builds the mathematical formulation of the model's optimization problem and corresponding constraints. And then the model actually kicks off its first optimized solve year, where we see here the iteration between the ReEDS optimization of the energy system to meet demand and other constraints, and the PRAS resource adequacy assessment that determines whether the system ReEDS built actually meets desired resource adequacy thresholds. Like we mentioned earlier, the cycle will iterate for each solve year until ReEDS is able to build a resource adequate model, or if the maximum number of iterations is reached, at which point ReEDS will then move on to the next solve year. And then after the last iteration of the final solve year, ReEDS will then send the resulting systems for each solve year to a host of post-processing scripts that produce various reports, figures, and tables of the ReEDS output. Okay, I know everyone's brain's probably fried from the fire hose of information over the last 50 minutes, so I promise this is my actual last slide before I finish. I wanted to end with some closing thoughts about how I would describe ReEDS as a model at the highest level. So I would say that ReEDS is a powerful tool for assessing the various drivers and potential futures of the US electric power sector. It's able to simulate capacity expansion of the lower 48 United States and its subregions at a high resolution, both spatially and temporally. The model allows for a high degree of flexibility in the development of its scenarios that users can explore, proven by its record of over 120 plus publications citing the model. It's a contemporary open source model. New versions of ReEDS are released to the public repository on a monthly release schedule, complete with release notes outlining all the new model features and changes, comparisons from previous versions, and bug fixes. And lastly, it's a living model. What I mean by that is that the model is supported by a team of over 40 developers and analysts working every day to make improvements to both, or to model capability, efficiency, and transparency. Speaking for the entire ReEDS team, our goal is to continue developing relevant model capabilities and providing the necessary tools for the audience to answer critical and emerging questions about the future of the US power sector. And I hope you guys get a good sense of that from both this presentation as well as the ones to come.